Hello everyone, welcome to Ground Zero AI, and we are going to continue with the transformer lectures. And today we are going to focus on RNNs. Today we are going to focus on attention. Okay, so before we go to attention, if you remember the problems with RNNs, right? So what we aim to fix here is the problems with RNNs, whatever the problems with RNNs are. So after RNNs, there is something that came into play, that is sequence to sequence. Okay, so what sequence to sequence did was basically, let's say there is this word. Let's say my job is to translate from English to Hindi. Okay, it will be how no, I am. Let's say the word is I. Then let's say am. Let's say then good. Okay. So what sequence to sequence RNNs did? Okay. So what basically sequence to sequence RNNs did was it sequence to sequence, not RNN, sequence to sequence model did was basically have two RNNs. Okay. So basically what they did, they had a hidden state. So basically three hidden states from the three, what do you call it, the three words, and both, okay, so this part, okay, is, this whole part is my encoder part. Okay, so it encodes it. Okay, so it first encoder gives two outputs. Okay, one output is the decoder state. Decoder state, the first decoder state, that is S0, and the other one that you get is basically it has two outputs. Okay, let me draw this first. Okay, so you first get a decoder state, and then you get a context vectors. So what is this context vector? Context vector is basically the main context. Whatever we taught in the problems with RNNs, you saw the context was getting lost, right? So from this encoder RNN, we are getting two outputs. One is the decoder state and one is the context. Okay. Now if you notice, everything will have only a single context. There are no different contexts. Like the whole RNN will only give a single context, that is C. And now from the decoder state, what we do is basically we are getting, let's say, the first decoder state. So that is S1. Okay. And from now what we do, the decoders, from the decoder state we get S1, and into it we feed the first input. So that is a start token, right? Because the sentence will start with a start token, right? So what will this spew? This will spew the word I am good is what? Theek who? So it will be theek. Okay. Now we'll use this input theek as the input for this output theek as the input for the next. And this will come here. And using this S1 state, we also get this one to be the S2 now. Now using this theek, what will be the next token? Who. So theek who. Now this who will become the input for the next one. Okay. And this one will be S3, and the final token will be what? The end token. So this is how the sequence to sequence learning in a short thing works. Okay, basically now if you see, this one has no context from the hidden state, right? Like you should have some context from the hidden state, no? So from this context vector, the context vector is linked to every one of those. So my inputs are always the earlier hidden state. Whatever the earlier hidden state is, the context vector and the current input, whatever you're giving, and you're getting this. Okay. So like this, we can do easily do machine translation. So this is sequence to sequence, and we explain to you why this is really bad for longer contexts, longer context. So we had already explained it to you. So we are trying to going to solve this using attention. So our aim is to cover two attention: the actual attention, that is the Bahadanau attention. The second attention is the attention that you learned in a layer. Basically, the attention that we use in self attention, or whatever you use in the attention, is all you need paper. So these two are different. So we will go into detail of how these work. I have explained to you how sequence to sequence works, and now we'll try to fix this. Okay, so let's now start how the attention works. We'll closely by making attention. How do we do this? So first we have a simple RNN layer. Okay, so the input is there. We have a hidden state, and from that we are getting a initial decoder state. Okay, so let's this be the S0. Okay, this is my initial decoder state. Okay, so what we do is that we find something called an alignment score. What is an alignment score? So alignment score is derived basically from the previous state and the hidden states. So the alignment scores are written as, let's say, E1, E2, and E3. These are your alignment scores. What are they? I explain it in detail. Okay. So this, whatever, how are they formed? They taken input from H1, H2, and H3. Okay. And alignment scores are done for each for each output we are working with. So since we are trying to first find the first word, right? So for example, from the input of start, we want to find the word thick, right? So this is our first alignment score. So this is our first alignment score. This is our first alignment score. So we understood something. We have to find alignment scores for different words in their context. Okay, so this is done. Now how the alignment score is also linked to the previous state. Okay, so now how do we find out the alignment score? So the alignment score is basically what? Let's say E of Ti is nothing but a function of my Hi and my St minus I. T minus 1, sorry. So what alignment score in essence is? It's a function of the hidden state it is corresponding and the previous decoder state that we're working with. And what is this function f, you must ask? Function f is a simple perceptron layer. So what is perceptron layer? We will link you a reference for this. So this is a simple perceptron layer that is working here. Okay, so this is the first step of attention. We made a alignment score. After we have reached the alignment score, we will find the softmax of each of them. Let's say softmax. So after we have reached the alignment score, we will find the softmax of each of them. Done. Now why do we do this? Because we are trying to normalize the values. So now finally we need to find the context vector, as we said. So here what happens is that the context vector is basically we do a matmal. We do a matmal of this with the hidden state. Wait, let me draw this correctly. Okay. Wait. Yeah. So here we are doing a matmal. I'm not drawing. Wait. Let me draw this correctly. so that you guys can follow. So this is a matmal. So 5, yeah. So this is a matmal we are doing. So with the hidden state, sorry, not the with the X, it will be with the hidden state. So we are matmaling the e-score softmax with this, and we will do the same for every one of them. I'm not drawing the arrows again, but you can understand that we'll do every one of them. And whatever result we get, okay, whatever result we get, we are going to add them. The result will be added. Okay. So after adding them, whatever vector we'll get, okay, let's say, let's bring this S here. This will be my first context vector. First context vector C0. C0. And let's attach this here. Yeah. So this is the basic part. Okay. If you understand it, this is the main part that we are going to do. Now, the second part is exactly the same. There is nothing different. Then second part, what will be the second part? We will have of course, we'll have some S1, that is the first decoder state, and this will be linked to S0. The input will be coming from C0, and there will be some input from here. Let's say the input is the start vector, the start token, sorry, the start token, and the answer will be teak. Okay, so this is how the basically the first iteration worked. Okay, worked fine. Now when this is done, now what you have to do is that S2 is there. Do you think you are going to use the same context vector? No, no. You are not going to use the same context vector. You find the new alignment score. How? Let's delete everything. Let's delete everything. Let's delete everything. This part is same, so will not change. So the new alignment score will be with respect to 2. This will be 2. This will be 2. Okay. That means what? We have to combine it with ST minus 1 or S1. So it will be linked to this now. Wait, let me draw the arrow correctly. So it will be linked to S1 now. Okay. Now again we'll calculate whatever the addition of this will be. And from that we will get our C1. And that C1 will go into S1. And then the thick will also go in there. Then you will get this output of who. If you know, so we have to do the context vector. We have to we get a new context vector for every word. So in an essence, we are not losing context here. Like we were having in RNNs, a sequence to sequence, whatever we were facing, we have solved the main issue. Okay, so we have to keep doing it till the end. So this is what we called the Bahadanu attention that was covered by Bahadanu et al. At his paper. So this was the main idea that was there. Okay. So this is Bahadanu attention. Now how can we make it better? How can we make a attention layer of sorts? How can we do it like that? So let's try to attempt that kind of problem. Now, since we are done with attention, now let's try to make it into something which is mathematical. We have watched it as something which was very, how can I call this? Like, let's say we are we taught it as in a very intuitive way. So now we have to learn the abstract way, how math works. So what is my input vector? Okay, what are my inputs? Let's discuss that. So let's say my input is X. Okay. So my input dimensions will be, let's say, some n cross d, just for We are declaring this as this. Okay. So why n cross d? Because we are inputting n words and d is the dimension. D is the dimension of whatever embedding we are using. We don't know what embedding we'll be using, but let's say the dimension is d. And let's say q, the query vector, is basically our basically query vector here is the st minus 1. Okay. So whatever the st minus 1 is. So we are this is our previous hidden state basically. So whatever the query vector is, let's say let's name it q. The query vector, let's say it has the dimension dq. Since you know the hidden state will be a single 1D vector only, so it will have the dimension of dq. So then we are using the function was our MLP, multi-layer perceptron. Then the alignment score was nothing but the function into the function, the query, and the xi, right? And finally, my attention weights is my softmax of the alignment score. Okay, I forgot to say something. I forgot to say something, but I'll add it in the editing maybe. Is that the before getting the context score, whatever the addition like thing you get is called the attention weight. Okay, that is where the name came from. That is the attention. Okay, and my final context output is the whatever the sum of the attention I is with respect to xi. Because it will change, right? For different xi, it will have different attention, right? So this is how we think Bahadanau attention is. Now we have to shift it to something new. Let's start. So our input will stay the same only nx cross d. Now q vector, every time the query is changing, right? The hidden state is what? First S0, then S1, then S2. So what we if we make a matrix of that, right? If we make a matrix of that? So I'll change my query vector to be q of nq into dq. Simple. We are just taking n queries at once. That's nq number of queries at once. That's why we're changing it to a matrix. And we can do the calculation in one single matrix multiplication. That's what we are doing. Okay. So we are now changing the function to be a scaled dot product. Why? Why do we do this? Why not SAP MLP? So MLP function is what? MLP function uses one dense layer continued by any activation layer. So we usually use softmax in MLP. Okay. So why are we not using softmax here? That might be a good question here. So whenever let's say we are doing softmax before let's say finding the alignment score or anything because we are applying the sorry, whenever we are doing the MLP, right? So there will be some dot product before that. Before the dense layer is before that, no? So there will be some dot products. So after the dot product, when we will do the softmax, the dimension of the vector is very large in this case. For example, in the case of GPT large, it can cross 16 or 1600, more than 1600. So the softmax function will create a vanishing gradient problem in this case because the value will get really large of the x and the softmax value will depreciate and it will become very close to zero. So we are getting a vanishing gradient problem here. So we are not using anything that uses softmax in this case. So we are making something called a scale dot product. Scale dot product is nothing. Let's say we have A and B. So we do A by B and scale it. Okay. Scale it by dividing it by root of the dimension. This is the basic logic of scaled product. So in our case, what will it be? We were using xq qi. So here the scaled because of the scale dot product, what the final thing will become? Why is Grammarly disturbing, man? Yeah, wait, I have to write this again. N cross D, then Q is NQ cross DQ, and then my function is the scaled dot product, right? And now scale dot product gives me what? That that is basically my x. Whatever my xi is, q dot xi by root of dimension of q. What is the dimension of q? That is my dq. Okay, simply. So this is my function now. This is the first change, major change we did after the query thing. Now, what will be my alignment score? Alignment score, my spelling sucks really hard. My alignment score will be what now? Q I dot x some xj, right? Okay, so xj by root dq. So that is the basically whatever the scale dot product is, right? This is my alignment score. Now we can do one interesting thing is that we can find the full matrix of the alignment score just by doing this q dot x transpose. If we do this, we find a matrix of size n. It will be, wait, since d and dq are almost, d and dq will be same, right? Otherwise you can't do the matrix multiplication. So d and dq are same, so it will be nx cross nq. I think this is right. No, no, no. Sorry. I said the reverse thing. NQ cross NX. Okay. So this will be my alignment score matrix. Okay. So how to find the attention scores now? Attention will be my soft max of the E matrix. Okay. Which is simple. And my output now will be basically what? Whatever my A is. Let's say attention is A into x, the matrix multiplication of x, right? A into x. We are actually, what do we do in output? We take every attention and we add it, right? So if we just matmul it, what will happen? So we will multiply every attention with x, every softmax value with the x. We are matmulling it and then adding it up. So my output will become a dot x. Okay. Have you understood this? This is how we changed the basic attention into something different. Okay. Now I drew a diagram to explain this. I will show you the diagram. Let's delete this. And this is the diagram. Okay. So what are we doing here? See, here is the E matrix. Okay. The, the alignment score matrix. So from x1, yeah, so from x1 we are getting k1, k2, k3. This is my first hidden state values. Okay. From the W, we are taking some weights wk1, wk3, wk2, and then we are matmulling it with x1, x2, x3 to find some k1, k2, k3. These are my key values, which give me the key values with respect, and also the query values are my input, as I told you earlier. Okay, it's better if I show the text I said here. No, that would be better. Yeah, this text. Okay, so see, so here my query vector is n cross d, and here is my x n cross d also. So then what we are doing, the alignment score is what? Q into xj. My xj is coming as some k, the key value. Okay, the key value, and we are getting the alignment score here. After we have found the alignment score, we are doing the softmax to find the attention value here. We have found the attention value here, and here is the attention value. And after the attention value is there, what are we doing? We will multiply x with attention. So what? See, we have made some value v, and we are multiplying it with a to find the final output of y. You can see now the process is being covered in a single stage. You don't have to calculate the context vectors every time. And you have actually, if you notice something, right? If you see the attention is all you need paper, right? You have kind of solved it. You have kind of written the attention there. Now, what's different in the attention to all you need paper is that it is self attention. As in, like here, since the queries are something that is different from X, so it's not like that. Here, if in the attention is all you need paper, what happens is that the queries are related to, wait, let me draw it correctly. Queries are related to the X values through a weight. Of course, I'm not writing it, the weight q1, wq1, wq2, wq3, and that is why that kind of attention is called self attention. Okay, that is how the self attention comes. So if you remember, what is the attention formula from the paper? Attention is softmax of q cross x transpose by root dk. This is the into value. So see, we are doing kind of that only. See, q into x transpose by root dk, my alignment score, softmax into value to finally find the answer of attention. See, that is how we solve the attention problem very intuitively. So this is what there is. And there's a fun story, like people ask, why do we say it query key value? So there's a fun story. I am quoting this and paraphrasing this directly. The key value query concept is analogous to retrieval systems. For examples, when you search for videos on YouTube, the search engine will map your query against a set of keys and associated to some videos in their database, and then present you with the best matched values. So see what basically we are doing. Okay, this x will be k. Sorry. This is the actual attention formula. So we are inputting some queries. Some queries go in and it gets checked with the keys in our database. Think it of like this. And then this is our some value matrix we get. And then we give the best values we have got with the values present in our database to find the best answers here. So this is the main intuition behind key value, why the name was given. It's nothing related to this, but it's a fun way how you can think this. So with this, we have covered what is attention, self-attention, and how attention works and everything in detail.